I'm the chair of this session, and post-quantum cryptography in software, the first one. And the first talk will be on vectorized and parallel computation of large smooth degree isogenies using precedence-constrained scheduling. Okay, so it's a work from multiple institutions, and Kitty Pong and Palakan of the University of Waterloo will give the talk.
Thank you very much, Professor, for the introduction. So this work is a joint work with Professor Warapong from the University of Tokyo, Professor Francisco from Sinvest Hub IPN and TII, and Professor Anwar from University of Waterloo. Okay, for the first thing, I would like to give you the quick overview of the contributions of this work. So various isogeny-based crypto system, which is whether it will be encryption scheme, hash functions, VDF signature scheme, they require, some of them require the costly computation of large smooth degree isogeny. And in this work, we propose two low latency parallel software implementations utilizing precedence constraint scheduling or PCS algorithms. So we consider two implementation settings. The first one is we consider multi-core parallelism. And the second one, we consider AVX512 vectorization with multi-core parallelism. And by the benchmarking, we see significant improvement when using scheduling compared to previous work which did not. So let's get started. So for the outline for this talk, we will start with some backgrounds on isogeny and scheduling, and then we move to two of our implementations, and then finally some conclusions. Okay, isogenies. And isogeny, denoted by phi from elliptic curve E to E prime, is a surjective morphism or mapping with a finite kernel. And in addition, an isogeny can be uniquely computed from the original curve E and its kernel by the result of value or values formula. So as an example here, we have this curve E, and suppose we want to construct an isogeny from this curve. And if we specify the kernel to be this set of 2 points, the set of point at infinity and point 0, 0. So what we can do is that we can uniquely determine that the image curve E prime will be this curve. And the definition of the isogeny, the mapping, can be defined something like this. So this is the isogenies. So for the isogeny used in cryptographic protocols, we consider isogeny with large degree. And in this work, we consider the computation of degree L to the E isogeny. This means that the input for the computation will be the curve E and 1 point R on E. And the output we want is the image curve E prime and the isogeny phi from E to E prime, such that the kernel for the isogeny is generated by the point R, and the size of the kernel will be L to the E. So this parameter L and E will be public. So by the result of the Feld et al. In 2014, it is best to decompose the original large degree phi as a chain of smaller degree L isogenies, and we will decompose it into E of such small degree isogenies. So here first we have the first isogeny phi 0 from E or E0 to E1. The second one, phi1 from E1 to E2, and so on. And the last one, phi E minus 1 from E sub E minus 1 to E sub E, which is our target curve E prime. So for a clearer picture, I will give you a concrete example of how this thing works. So we will look at an example when E is 6. So let's see. So first we have this input curve E or E0 and the input point R or R0 on E. So the first thing we do is that we perform a scalar multiplication on R0 and we obtain the new point. We perform this scalar multiplication E minus 1 or 5 times in this example, and we obtain this new point R0 prime. We use this new point to generate the kernel for this first isogeny phi0. So we can define phi0 using this point R0 prime. Next, for the next isogeny phi1, we first maps R0 on E0 to R1 on E1 using this isogeny phi 0. And then we again perform some series of scalar multiplication, this time 4 times, until we obtain R1 prime. For R1 prime, we use it for the kernel generator for the next isogeny phi 1. And then we follow this same fashion until we reach the last kernel generator R5 prime for the last isogeny phi 5. And after that, we reach the target image curve E6 or E prime in this example. So for the analysis after this, we will stop at the last kernel generator R5 prime, and we will work on this nice triangle. And so this is one way that one can do the isogeny computation, but this is not the only way that one can do. So because here we have this relationship between these two operations, they are commute. So what we can do, we can come up with many ways of doing the computation. For example, consider this point R1 prime here. One way is that we do the computation from R1 with lots of scalar multiplication. Instead, we can do the isogeny map from the corresponding point on the curve E0 to obtain the same point R1 prime because of this commutative property. So we have lots of ways to do the same computation. And to formalize, on the left here, we have the graph of all possible operations. And on the right, what we want to have for the computation is a subgraph of it. We call these things strategies. And formally, strategies are subgraph of those on the left, where all Ri prime or the kernel generator or those on the diagonal line are reachable from the input, this point on the top left corner. So here we can define several ways of doing the computation for large smooth degree isogeny. So we move to the first simple computation setting of single core computation. So here, because we have seen that we have various ways of doing the computation, which strategy or the graph we use for the computation. So for the simplicity of this talk, let us assume that both operations take the same amount of time. In the paper, we consider the setting where they are different, so please check it out. So under this assumption, the single core cost for the computation is the number of arrows in the strategy. So let's see here, the one on the left, it has 18 arrows, so it has cost of 18, and the one on the right has cost of 16, and we would prefer the one with the least cost possible. And by the result of the paper from 2014, optimal strategies or those with least cost can be constructed using a dynamic programming algorithm. So for this setting, we can consider that this problem is solved. So we move on to the more intricate setting of multi-core computation. So in this setting, a strategy can be parallelized in many ways. Let's see this example. We're going to do the computation using this strategy when we have capital K equal 2 cores. So one way that we can do is that we can perform this operation in step 1, 2, 3, 4, and now we reach the first kernel generator, and we can do the first isogeny map to the next curve. We can choose up to 2 operations to perform here. Let's say we choose these 2 in step 5. So what next? We can choose these 2 in step 6, 7, 8, 9, 10. So we finish the computation in 10 steps. But what if instead we choose these 2 in step 5? Well, we can do these 2 in step 6, 7, 8, and 9. So the order of operations plays important role here. So in the multi-core setting, we have 2 questions. Which strategy should we start with? We call that strategy construction. And how should we use it or parallelize it? And we call that one strategy evaluation. And in this talk, we will focus on the second question on strategy evaluation. And in literature, the first evaluation technique proposed was in 2018 by Hutchinson and Karabina. It is called per curve parallel or PCP. And PCP, the rule of PCP says that for each column from left to right, we perform the down arrow scalar multiplication sequentially, and then perform the right arrow isogeny map in parallel. And see, we have this quick animation of how PCP works. So you can see that it will go from left to right, a bit slow, but because of its simplicity, I think to the best of my knowledge, they are used for implementation in all existing implementations. And also by its simplicity, optimal strategies under PCP can also be constructed using dynamic programming algorithm. There is also another technique proposed by the same paper called consecutive curve parallel, or CCP, which can be considered as an improved version of PCP. So this is the only evaluation way available at that time. So in our previous work, we try to improve this thing, and we reduce this evaluation problem into a scheduling problem. So here's a problem. We call it precedence constraint scheduling, or PCS. The problem says that we are given a task dependency graph, something like this, and we want to schedule our tasks to be done at earliest. So vertices represent tasks to be performed and edges represent dependencies. And the output we want is a scheduling which describes which tasks are done in each step. So from this graph, suppose we have 3 computation cores, we can come up with this first scheduling S, which finish everything in 4 steps, and another scheduling S prime, which is done in 3 steps. So the goal here is to come up with an optimal or at least short scheduling for the computation. And by this, in the previous paper of us presented at ACISP 2022 in Australia, we proposed this PCS technique. So here from the strategy, given strategy, we first transform it into a task dependency graph. And then we apply 2 scheduling algorithms. They are by Hu and Kaufman-Graham. So those algorithms specify which task should be done first and which task will be done later. And by the scheduling, we can come up with how we evaluate the strategy. So now we will move to our implementation, the first implementation which uses only multi-core parallelism. So to the best of our knowledge, the state of the art uses PCP for its implementation. So we implement PCS technique in software based on SIGE protocol, specifically SIGE P751. They are in C implementation, and the synchronization handling is done using OpenMP API. And we consider 2 execution environments here. The first one will be system with up to 4 cores, and the second one, we will use 4-core with vectorization technology AVX512. So for the first multi-core implementation, we just extend our PCS framework 1 step further, because here when we obtain the evaluation, it is natural and straightforward to change that evaluation into C code using OpenMP. And by that, we do the implementation. We use the pre-computation technique proposed by Vasquez et al. From last year, and compare our results, which use PCS, with that paper, we use PCP. So we see that we have the benchmarking results for 2-core, 3-core, and 4 cores. This number here are shown in million CPU clock cycles. And we see that the best improvement we can have here when changing the evaluation technique can be up to 14.36%. The next implementation we will deal with AVX512 technology. So a quick recap on that. For Intel's Advanced Vector Extension, or AVX512, the instruction considers 512-bit vectors or bit array as 8 64-bit elements. The instruction will perform 8 64-bit operations within a similar time as 1 64-bit operation. So here, as a quick example here, I showed you how it works using the 64-bit addition as an example. But in general, in the implementation, our number is not just 64 bits, it's longer than that. So we have to divide it into blocks of 64 bits. And there are also various ways of using vectors. So here, suppose we have 8 pairs of operands or operations to perform. So here we can put 1 block from each operand into 1 slot of the vector, resulting in 8-way use of vector. But suppose we only have 4 operations to perform. We may not want to use just 4 slots of the vector. Instead, for more efficiency, we can use 2 slots for each number, resulting in 4-way. And similarly, we can come up with 2-way and 1-way use of vector. And because of this, it introduced a bit of complications to the optimization process. So in this work, we would like to point out that it is the first to utilize vectorized and parallel computation together for isogeny computation. And some things to consider for the optimization are that we have different ways of using vectors, 8-way, 4-way, 2-way, and 1-way. And they come up with different amount of time used in the processing time. And moreover, all 8 vectorized operations within the vector have to be the same, but it can be different between cores. For example, the first core may perform 8-way isogeny mapping, while the second core perform 2-way scalar multiplication. So we have like lots of options of how to schedule operations. And the original proposal of PCP and PCS does not consider this execution environment. So we have to propose the modified version of PCP and PCS to accommodate this execution environment. So, and here is some benchmarking results from our software. So we compare our result with the PQ Crypto SIDS library by Microsoft, which use just 1 core sequential computation, no AVX. And the second work is by Cheng et al. From last year CHES, which used 1 core with AVX technology. So here when we move to multi-core implementation, when we have 2 core, 3 core, and 4 core, we can see that the running time reduces. And when we have 4 cores, the reduction can get up to 34% for the execution time, which is quite significant. And lastly, for the conclusions of the talk. So here in this work, we propose 2 low latency parallel implementations for large smooth degree isogeny computation, where we use the PCS or precedence constraint scheduling algorithms. And both algorithms show significant improvement in practice. For future works, we have several directions on how we can improve our current results. The first thing is that we would like to extend our work to other settings, such as C-side or ski-side, or the use of AVX2 or 256, which is more widely used here, and also the implementation of our technique as a hardware, etc. Second, we would like to adopt more cores for the implementation and also faster arithmetic packages for the opportunity to obtain faster implementation. Next, we would like to work on more precise cost functions that consider architectural effects for the implementation, such as memory access and also the synchronization costs between cores. And lastly, we would like to study the optimality of strategies and evaluations used in various implementations and try to improve that bound. And that's all for my presentation. Thank you very much, and I'm happy to take any of your questions.
Let's thank Kitty Pang, and there's lots of time for questions. Anybody? Yes.
Hello, thank you for the talk. Regarding your new PCS strategy, is there a memory overhead?
Okay, can you repeat the question again?
Oh,
memory overhead.
Yeah. So for now, we have to store the description of the strategy kind of like as a pre-computation in the source code. So it is a bit of overhead. We didn't measure that like formally, but I think this is a bit of overhead there.
And also regarding the points that you need to store for computing the isogenies, do you need to store more points with PCS?
Can you repeat it again? Sorry.
Do you need to store more points with your strategies when computing the isogenies, the sub-isogenies?
Yeah, you mean the intermediate points during the
Right.
computation, right? Yeah, we didn't consider that like formally, but yes, that's one overhead of our algorithm compared to using like more simple ways.
Okay,
Yeah.
thank you.
Thank you.
Other, yeah.
Thank you very much for a very nice presentation. So follow up on that question. So I'm wondering, like, so you separated into two parts, like how to construct, like how to, like construction and evaluation. And you, like, my understanding is that you gain from evaluation part, and then to construct this thing, what would be like the overhead or the pre-computation, and how, like, I mean, if you compare construction from different work, like how that compare?
Okay, so actually I didn't mention how we came up with the strategy in the first hand. So let me talk about that a bit. So to the best of my knowledge, again, we use the result of this PCP. So we have optimal strategy under PCP. So we use that for the construction. So we use the optimal strategy under PCP, but with different ways to do the evaluation. So to search for the good strategy in the first hand, we have to like go into the search space and do some kind of like random search, kind of like maybe Monte Carlo search, to come up with some strategy and do consider if that's good enough, and we choose the best one. So it takes quite some time, but it's just a one-time process, right? If we can get a good strategy, we can use it many times. So it's a bit long to come up with a strategy, but it's just one-time process. I'm not sure if that's answered the question.
Partially, thank you, but we can take it offline. So may I ask another question for the chat? Yeah, so the second question would be, so you mentioned about like 2 cores, 4 cores, and later on you mentioned about different ways of parallelization, and how would that scale? Like if the number of cores increase, or if you have many ways to parallelize, like how would that how the performance scale, either the overhead or the gain, that reduction gain that you
we give a bit of those analysis in the paper. So maybe from this table, you can see that when we had from 2 to 4, 2 to 3 and 3 to 4, we do not gain that lot of speed up, because maybe there is some limit in the amount of parallelization that we can apply to the computation, because you can see that the graph, the dependency graph for the computation is quite complex. So we do not achieve as much speed up as we want. And I think in the paper, even then we have like infinite number of cores, we can gain maybe up to only 3 times speed up for using parallelization. So maybe we will get to the limit when we add more cores.
Thank you very much.
Well, I have a question, which is, now you know that there are many architectures where they have one large core and one small core. I mean, or many large cores and many small cores. And your description is that you assume all the cores are the same. Is it possible to extend this to asymmetric cores, where, I mean, some of the computations can be done on the cheaper cores using less power, and is that possible?
Yeah, I think that's possible. Thank you very much for this interesting question. So right now we work on only simple cost function. Of course, we work on like some abstraction of those computation as a function, and we try to optimize those function mathematically. So if we going to more complex setting of the computation, we have to like try to formalize that into like more accurate cost function, and that's one way that we can do. And maybe we can do that in for the future works. Yeah.
Thank you. Any other questions? And anyone online? I guess I don't see anything online. So let's thank Kitapong again. The next speaker is Frank Custers. I'm sure I'm butchering his name. And he's going to talk to us about the ProtoChem on embedded devices. And let's just welcome Frank.
Yes, thank you for the introduction. Thank you for the introduction. So this work I did together with colleagues from NXP as well as a student from Radboud University. So first of all, why is ProtoChem still relevant? Because it's one of the schemes that got submitted to the NIST post-quantum competition, where it got eliminated as a third-round finalist. However, due to its more conservative approach at security, it's still of interest to some European authorities, such as the BSI and ANSI. And this has now also led to a submission to ISO for standardization. This means that we should now already start preparing implementation details. And the one thing we look at is reducing the memory usage of ProtoChem. So as a recap on what is Frodo or ProtoChem, as I will be using these two terms interchangeably, it's a lattice-based key encapsulation mechanism. So if you're perhaps familiar with Kyber, it's very similar to this. But the main big difference is that ProtoChem is based on the plain learning problems. That means that there's no added ring structure to this. Now, in this figure, you can see all the operations that happen in the decapsulation algorithm. And since ProtoChem uses the Fuyusaki-Okamoto transform, or the FO transform, it also contains all the operations from the encapsulation algorithm. And furthermore, the key generation also uses a very similar set of operations. So throughout this talk, I will only use this decapsulation as an example, but note that all the tricks and all the optimizations I will show will have either similar or analogous results in the two other algorithms as well. So the issue we want to solve is that all previous implementations are simply too large for many use cases. For example, IoT applications which uses devices which are very memory constrained. And this can already be seen in the PQM4 implementation, because this implementation only contains the smallest parameter set, so NS640, because the bigger ones simply do not fit on some of the associated development boards. So one of the first things we actually did is extend this implementation to get some idea of some benchmark results for the memory. So since ProtoChem is based on the plain learning with error problems, the main building blocks are large matrices containing integers. And these integers are always 2 bytes large. So I've highlighted here in red where all these matrices show up. What we can see from this image that we have already 6 of them that are of size n by n bar, or n bar by n, which are the same size, of course. Here n bar is always equal to 8, while n depends on the parameter set. So we have 3 parameter sets, and even for the smallest ones, we see that, so for the smallest one, we have n is 640, and we see that already a single matrix takes 10 kilobytes to store. And if you go up to the higher parameter sets, so for n is 1344, a single matrix already 21 kilobytes large. Now we also have this even bigger matrix, which is the public matrix A. And this is generated either by AES or Shake, depending on the version of ProtoChem. So there's 2 versions and 3 parameter sets. And since this is an n by n matrix, if we had to store this in full, this would already take up in the range of megabytes. Now, the good thing is that when ProtoChem got submitted, the original authors included both a reference implementation as well as an optimized implementation. And the difference between these two is that in the optimized implementation, A is never stored in full, but it's rather generated on the fly, meaning that you only generate a few rows or a few columns at a time and store these. And this already has, of course, a huge impact on the memory usage. Now, Another very important work is this CHES paper from 2018 titled Standard Lattice-Based Key Encapsulation on Embedded Devices. And they already make some big steps in decreasing the memory usage, because what they, for example, do is they look at the lifetime of these large matrices, and they know that if they do not have an overlapping lifetime, you can reuse the memory locations. Another thing they do is they look at doing more things on the fly. So for example, the packing or unpacking of matrices in this case can be done on the fly. And unpacking happens, for example, when you obtain a matrix from the ciphertext or the public key. Another thing they do is that you can do sampling on the fly. And sampling in this case means generating the randomness with shake followed by Gaussian sampling, which Photocam uses a CDT sampler. And this then pairs nicely when you do this matrix addition on the fly, when you add an error matrix. So how do we improve beyond these works? Well, we show that you can do even more things on the fly. For example, when you have to compare large matrices, you don't have to actually store them both in full, but you can only compare a few elements at a time, and then you just store this flag that shows that when inequality occurs. Or we show alternatively, you can also just compare hashes of matrices, where we then use shake to do this hashing completely on the fly as well. Now, the main result from our paper come actually from how we do the matrix multiplication, so I'll spend a bit more time on this in a few slides. Now, results are twofold, because we ended up making two implementations, and the first implementation we call the low-cost version. Now, the idea here is that we want to optimize the memory as much as possible without having a significant impact on the performance. By performance here, I mean the runtime, so the cycle count. And this is characterized by still having to store one large matrix in full. So one large matrix, I mean one of these n by n bar or n bar by n. Now we go even beyond this in our second implementation, because here we do not store any of these large matrices in full. But this will come at a significant cost for the performance, because this means you have to reconstruct matrices, and well, this just makes it slower. However, as I will show for this implementation, there are time memory trade-offs possible, and this is why we call this version the trade-off version. Now, to realize these implementations, we use the PKM4 implementation as a baseline, and then we also include the ideas of these prior works. So next, I will give some more details about the matrix multiplication strategies we use. And note that we actually still use schoolbook multiplication, but our novelty just comes from the order in which we do the multiplications. So the most interesting one happens in this set of operations, because here, when you do this multiplication and addition, both the input matrices are large, but also the resulting matrix is large. And this shows you an idea of how this multiplication looks like. And for the low-cost implementation, so the first implementation I mentioned, we store one matrix in full. So here we choose to store this B double prime in full. However, for the two other matrices, so S prime and A, we only store an 8 by 8 block in full, or only an 8 by 8 block. And the easiest way to explain our multiplication strategy is by considering two nested loops. So you have an outer loop and an inner loop. Now, in the outer loop, you fix one block of S prime, and then in the inner loop, you go to a set of 8 rows of A as blocks. Now, every time you compute one of these new blocks of A, you compute all 64 inner products between the two blocks of S and A. And these inner products are just of size 8. And then you accumulate this result to the corresponding place in B double prime. Then in the outer loop, you go on to the next block of S prime, as well as the next set of rows of A. And then you repeat this whole process of this inner loop again. Now, what happens is that in every iteration of the outer loop, you update every single value of B double prime, and this is why we still had to store this in full. Now, there's two issues with this multiplication strategy, and both of them involve this S prime matrix. The first issue is that it's not by default easy to generate these blocks of S prime, because the way it is defined is that you generate the randomness of S prime from one shake call. So it's one long output, but then in the row order. We actually want to access it in the column order. So what we do is we do a pre-computation step, where we effectively go through this whole matrix, or generate all this randomness, we actually do not store this output. The only thing we do is we copy the shake state every time it's at the beginning of a new row. So after this pre-computation step, we have 8 shake states. And to generate the next block, we simply squeeze out the next few values from every one of these shake states. Now, the next issue is that we never store this as prime in full now. But there's a second multiplication where we need it, namely when we multiply it with this B matrix. Now, the way we solve this is by doing the two multiplications in parallel, meaning that every time we computed one of these blocks of S prime, so we did this in this outer loop, then we first do this whole inner loop to multiply it with the corresponding values of A, but we also now generate one block of B on the fly. And we can also do this on the fly because this is simply unpacked from the public key. So we do this also these 64 inner products of size 8 with B and accumulate this to this V matrix. Now this multiplication happens also in the decryption step, so we can also reuse this strategy for this multiplication. But as you can see, we do not store any of these matrices in full, so we also reuse this for a second implementation, which was the trade-off implementation. Now, for the other multiplication, things start to get a bit tricky in this implementation, because as I mentioned, we do not want to store any large matrix in full, and then this means we need to do this comparison completely on the fly. However, we cannot reuse this matrix multiplication strategy for this large multiplication anymore from the low-cost version, because what happened there is that in the iterations of the outer loop, you actually update all the values. So now we have to change the strategy such that we fully compute one or a few elements of B prime before moving on to the next one. So the way we do this is we fix one row of S prime, and now instead of going to a set of rows, we now go to a set of columns of A. So now in the inner loop, we go through a set of 8 columns again as 8 by 8 blocks and do all the possible inner products with this row of S prime. Then in the outer loop, we keep the same row of S prime, but we go into the next set of columns of A. So every time we do this iteration of the outer loop, we have computed exactly 8 elements of this B double prime, and we immediately already have to do this comparison with B prime. Now, there is a big issue with this, and that is that after we finish this outer loop, we've actually only computed one row of B double prime because we only had one row of S prime. So we actually have to repeat this process a total of 8 times. And this means that every time we do this, we have to reconstruct A completely. And actually constructing A is the bottleneck of FrodoCam. So this will have a very significant impact on the performance. But there is a trade-off possible here, because instead of only doing one row of S prime, so compute one row of B double prime, you can do 2 rows or 4 rows. So in general, if you say we have a trade-off parameter T, so we do T rows at a time. This reduces the cost or the performance cost to generate A to 8 over T times. But this does increase the memory usage, because now we have not 2n bytes for S prime, but T times 2n bytes. Now, there's another big issue with this strategy, and that is that it simply does not work with the shake version of FrodoCam. And the reason for this is that in the shake version, A is generated as a full row from one input. Now, this input consists of a row index, so that ensures that it's unique, as well as the seed of A. Now, this means that if you want to generate a column of A, then you actually have to recompute all the previous columns to the left as well. Now, one way to solve this would be to store a shake state for every single row and then just squeeze out the next value to generate a column. But this is not feasible because a single shake state is already at least 200 bytes large, and you cannot store n of these. So what we actually propose is a tweak to the specification, where our approach now is more similar to the AES version, where instead of generating a full row, we only generate a subset of this row. And to do this, we also use this row index, but now also a column index. Now, the block size we suggest for this is 168 bytes, because this is exactly the rate of shake 128. And this means that the number of calls to the underlying catch-F permutation is exactly the same. So we also communicated this with the FrodoCam team, And we showed that even for their optimized AVX2 implementation, this tweak does not have any impact on the performance, because we showed it has less than 1% impact if implemented well. However, with this tweak, the trade-off version is again possible with the Shake version. The only difference compared to AES version is that we now not have an 8x8 block of A, but we actually have an 8x84 block of A, which is still relatively small. So now I can show you some of our benchmark results. And since we use the PKM4 implementation as a baseline, we also use this PKM4 framework to do our benchmarking. So we use both an STM32F4 discovery board, as well as the nuclei board to also be able to run the PKM4 versions of the bigger parameter sets. Now for the low-cost version, I only need to show you the memory usage, because the whole idea of this design was to do as many optimizations without having a significant impact on the performance. And this is actually reflected in our benchmark results, because what we saw is that our cycle count is within a 5% range of the PKM4 implementation. However, as you can see from these bar charts, is that in orange, our work uses significantly less memory compared to, for example, the reference implementation, the PKM4 implementation, but it's also smaller than this CHES 2018 paper. What's also interesting to see is that our memory usage is actually nearly constant between the three algorithms. And this comes from this idea that we only store one large matrix plus, of course, some extra overhead. Now for our second version, so the trade-off implementation, it's of course most interesting to see the actual trade-offs. So here on the x-axis, you see the number of bytes or the memory usage. And on the y-axis, you see the cycle count in millions. And I've plotted the trade-off implementation. So you see the 4 trade-off points, TS1, TS2, 4, or 8. And I've also included the results from this low-cost implementation. And from this, you can already see that taking TS8 is not a smart thing to do, because then both the memory usage is larger, while the cycle count is also slightly higher. But for taking TS4 is already an improvement, because you see the memory usage reduces from around 13,000 bytes down to about 11,000 bytes. But the impact on the performance is nearly a factor 2 to nearly 100 million cycles. And you can be even more aggressive and take TS2 or even T is equal to 1. And then you see the memory usage is around 3,000 bytes. But this has a very significant impact on the performance, because nearly 300 million cycles, which is a factor 6 compared to our low-cost implementation. So to conclude, I've shown you some of the key ideas of how we made these 2 implementations. There are, of course, a lot more smaller details to this, which include some more subtle optimization tricks. But with these 2 implementations, we show that it's possible to run all the parameter sets and all the versions of RotoCam on embedded devices, which are very limited in memory. And we show that this is even possible for some of the parameter sets and some targets without having a significant impact on the performance. And by using this trade-off parameter, we allow an implementer to set a specific memory target as well. Now, as a final remark, our code is not publicly available. However, in our paper, we describe all the steps in enough detail and include as many figures as possible that should help an implementer to implement these ideas as well. So thank you for your attention. And if you have any questions, feel free to ask them.
Any questions for Frank?
So you mentioned with Shake, it might be better to generate a row, only a partial row out of a Shake call. So would it also potentially be better to generate the A and or S matrices blockwise out of Shake, like do an 8x10 or 8x20 block of the matrix instead of a linear slice like that?
So which of the 2 versions do you, so in the low cost or the trade-off?
Well, I mean, I guess there would only be one standard, but instead of having like a narrow strip for the proposed modification, would it also work to have to generate a block at a time instead of a strip at a time?
I mean, that's kind of what we indeed suggest for the tweak. So, or do you mean like in the for generating these E prime and S prime?
Yeah, generating E prime, S prime, and or A.
Yeah, so that if you would include that, then indeed we do not have to do this pre-computation step. So this would be a possible solution. However, as I showed, we only did this in this first implementation, and it does not have an impact on the performance of more than 5%. So we did not want to change photochem completely. We wanted to try to be as close to the specification as possible. So we only suggested this tweak to how A is generated.
Okay, thanks.
Other questions? I guess I have a question, which is the most common PQM4 platform is the STM32F407 Discovery.
Yep.
And with your small implementation, could you actually run
Yes.
level 5 on the Discovery?
Yep, we did. Yes.
And so for trade-offs, you use something like maybe the STM32L5 Nucleo.
Mm-hmm.
Yeah, the one that has 640.
Yeah, that one has a lot more memory, and we actually use that to actually have like a baseline of what does PKM4 implementation do and what is ours. And we could simply not get this on this discovery board because it does not fit.
I see. So how many data points do you get out of the level 5, like L equals T equals what 1, 2, 4, 8, and like not any further, I guess.
No, so that's an interesting question. So we took 1, 2, 4, 8 here because we just used the divisor of 8 because we store the number of rows. However, in the key generation, it's slightly different because we actually reconstruct the height operand, which in that case is switch. So there we the trade-off parameter was actually a divisor of n because we reconstruct an n by n bar matrix there. So there we had a lot more options possible. But it is also in this one possible to do, for example, t equal to 3, but then you have to do like 3 rows, 3 rows, 2 rows. You do 3 times, so you win a little bit less.
I see. And anyone on the internet? I guess not. And no further questions. Well, let's thank Frank again. We go into the morning coffee break. Thanks, everybody.
Já už jsem měl svůj klobásu a dám si klobásu. Following aber das hat quasi keinen Anwendungspunkt.